The the incongruities in the Stern-Gerlach experiment led to the introduction of electron spin angular momentum, and that we'll take up here. In 1925, George Uhlenbeck and Samuel Goldsmith proposed an electron model as a rotating solid sphere of charge of a fixed radius, whatever the radius of an electron is, and that this could also give rise to currents if it was rotating, spinning, and therefore also have magnetic moments inherent in it. As a result, they had a model that looked something like this. They were still looking at sort of the Bohr type model. We know that in the Bohr model, the angular momentum was quantized in this sort. And then one could go through this process like before and get this expression for the angular momentum. If it's a negative charge, it would get a negative sign out front to indicate that the angular momentum vector and the magnetic moment vector were in opposite directions. But what Goldsmith and Uhlenbeck said, well, you can think of this as a lot of little pieces of charge that are rotating, and so each one of these form a current loop like this, and then we'd have to integrate that and add them all up. But it's going to give, dimensionally, has to give us this factor, and L vector, and the minus sign I've introduced here for the negative charge on the electron. And the only thing that's really different about this is that in the summing up all of these different sized current loops all over from very, very small to all the way out to the outside, one should just get a numerical factor here of little g, which is not degeneracy, but is called the gyromagnetic factor. For orbital electrons, little g is 1, but for a solid rotating sphere of charge, it's something different than 1. And also, they took to denoting this not as like L, they reserved L vector for the orbital angular momentum, and this would be the orbital magnetic moments. G would be 1, but one would have spin angular momentum due to the rotation of, in their case, the spherical electron. And therefore that the magnetic moment vector associated with an electron as a sphere is this with some numerical factor here. And S is an angular momentum, but is due to its rotation of this electron. There's only one issue with all of this that was sort of glossed over. At that time, they didn't really know, but nowadays we know all the experiments that have ever been done, there's nothing to indicate that the electron has any internal structure. So we have no experimental evidence that the electron is really any more or less than just a point charge. And their model is classical, but is based on an erroneous assumption, and that if the radius is 0, then there is no rotation of a mathematical point, and so for a point electron, it doesn't hold, at least that physical model. Well, this issue was solved by Paul Dirac, 1928, in which he developed a relativistic quantum mechanics equation, nowadays called the Dirac equation, for an electron. And what he found was that an intrinsic spin arose naturally from this equation. It wasn't put in by hand. The electron is still a point, but it carries an intrinsic spin angular momentum. And that spin angular momentum satisfies things that look like the regular, it is an angular momentum, so it looks like the equations associated with orbital angular momentum, except the total spin squared is S, not L, times S plus 1, not L plus 1, h bar, and associated with that is the z component of the spin, which is m sub f h bar. So these are really identical. They apply really to any kind of angular momentum from the quantum mechanical formalism. And then what Dirac also found was that S was 1/2. And if S is 1/2, well, m sub s goes from minus S up to S in integer steps. And so if you start at minus 1/2 and add 1 to it, you just get 1/2. And so you get these S quantum number for the magnitude or the total related to the total angular spin angular momentum squared is just 1/2. And then the m sub s here, the electron spin, is plus or minus 1/2. Well, this explained the results of the Stern-Gerlach experiment. If the magnetic moment of the silver atoms arose just from the spin of the electron in its outer shell. The electron is in an L equal to 0 state, so there is no orbital angular momentum, but electron can still have this intrinsic angular momentum. Mu z is this factor here, and in fact, the z component of force, if you plug all this in, m sub s is plus or minus 1/2, and so you now get if m sub s is plus 1/2, you get the line up here, and if m sub s is minus 1/2, you get the force deflecting it the other direction. And as a result, the intrinsic angular momentum solves two problems. It solves the fact that we only see a splitting into these two upper and lower pieces in the Stern-Gerlach experiment. And it also explains with Dirac, arises from my point electron, so it gets around this Uhlenbeck and Goldsmith hypothesis of a rigid electron rotating about its axis. Although the model is suggestive, and people still think of this as somewhat analogous to spin. Technically, the quantum state of an electron in an atom is characterized by 5 quantum numbers now. In result, we have N, the principal quantum number. L is the angular momentum quantum number. I would call it, if you want to be precise, the orbital angular momentum quantum number. M sub L, the z component of the orbital angular momentum, often called the magnetic quantum number. There's also the total spin, intrinsic spin of the electron. So spin, total, and this is usually just called the spin quantum number, or usually they don't even call this. But m sub s then goes from minus s to plus s in integer steps. So it goes from minus 1/2 to plus 1/2 in one integer step, and that is the spin quantum number. So technically, you should specify these in the following way. N, remember, goes from 1, 2, 3, etc. L goes from 0 in integer steps up to n minus 1. So once you know the energy level, then you can get the L, maximum L. And then m sub L, for any given value of L up here, goes from minus L up to plus L in integer steps. The S quantum number is always 1/2, and m sub s can be either minus 1/2 or plus 1/2. Well, since S never changes, it's always 1/2, it's usually left off. even though technically we should have injected in here between m sub l and m sub s, we should probably have s, but it's going to always be a half. And so people generally suppress that since it's always the same value. And they label the wave functions with this additional intrinsic spin of the electrons as psi n l m sub l like before, and they tack on the m sub s, which is either plus or minus a half on to the end. Well, we will continue this story next time. But that's how the spin quantum number arose historically.